No, it's just fine. She doesn't. Okay, why don't we go ahead and get started? Welcome all to SysLunch. That means you should stop talking. To SysLunch and the CNS lecture series. It's my pleasure to introduce Aruna Balasubramanian from the University of Massachusetts. She is finishing a PhD over the next few months and is going to be telling us about some of her work in wireless and networking. So with that, I'll hand it off to Aruna. Are you all...
Good afternoon. I couldn't hear my introduction, but thank you, Amin, anyway. The topic of my talk is architecting protocols to improve connectivity in diverse mobile networks. I just want to make sure that everybody can hear me. Yes. Hello?
Yes, they can hear you.
Yeah, okay. Hello? Hello? Okay, hi. All right, so, I'm Aruna Balasubramanian from UMass. I'm going to start this talk with a statistic. There are more than 2 billion mobile devices available worldwide. The most common of these devices are, of course, laptops and mobile phones. And here is another statistic. There were 500 million internet-connected mobile phones in 2008 alone, and this number is only increasing. But apart from mobile devices, such as mobile phones, mobile devices are also useful in several other domains. For example, you could have mobile sensor nodes attached to animals for monitoring animals. And mobile networks are also used to extend the reach of the internet to rural and developing regions. So not only are there a lot of mobile devices, but they are also used in a variety of very useful applications. The problem, however, is that the potential of mobile devices is not fully realized today. And this is because of two fundamental challenges. The first challenge is unreliable connectivity. The second challenge is energy constraint. And I've done work on both of these during my thesis work, but I'm today going to concentrate on the first challenge, which is that of unreliable connectivity. And so I'll probably spend the next 5 minutes describing why connectivity is unreliable and then move on to talk about what we can do about it. So mobile wireless networks are unreliable. So first of all, wireless networks themselves are much more unreliable than wired networks, but mobility adds to this problem. So now that you have mobility, now networks start operating in these diverse environments, starting from mostly connected networks to mostly disconnected. So what I mean by this is mostly connected, I mean that the disruptions last for a few seconds. You're almost always connected, but then you might be disrupted for a few seconds every now and then. For example, in cellular networks and Wi-Fi mesh networks. And then intermittently connected networks are those where disruptions can last a few minutes. For example, in semi-urban areas where there are coverage holes. And finally, mostly disconnected end of the spectrum is where you might be disrupted for a few hours. For example, in rural areas where there is no infrastructure. So let's look at some of these environments to see why disruptions occur and why the network is unreliable. And I'm actually going to start from the one end of the spectrum, namely the mostly disconnected network. These are also called as DTNs, or disruption tolerant networks. And the scenarios where they're most common are those where there is no infrastructure. So this is a common scenario. There is a village where and a user, and there is no infrastructure in the village. And there is a city where there is infrastructure, and I show this infrastructure with this Wi-Fi access point. Now, a user may want to send a web request or an email to the internet, to somebody on the internet, but has no way of connecting to the infrastructure. So what she does is waits for a vehicle to pass by, in this case a bus, transfers this data to the bus, and the bus finally transfers this back to the internet access in the city. And of course, on the way back, the email response or the web response is again transferred from the city to the village through another vehicle. Now, this may seem a bit far-fetched to some of you, but there's actually been a lot of work using this technology to improve connectivity in rural areas. So what I'm showing you is two examples, projects that appeared in the news. On the left is this project, Wi-Fi buses driving rural web use, where buses equipped with Wi-Fi is used to deliver web content in India. And on the right is this article about motorcycle messengers acting as email relay riders in Cambodia. So this is great. What's the problem? The problem is that you may not always have one bus that goes between the city and the village that can carry data. You may actually need to route data. And unfortunately, routing in this environment is extremely challenging. First, notice that there is no end-to-end path. So usually in traditional networks, you have an end-to-end path between the source and the destination. And intermediate nodes actually know who the next hop is going to be. But in this case, that's not how it happens. In fact, this user may not actually know who the next hop should be. And connectivity is unpredictable. So by that, what I mean is, suppose there's this other car that comes within range of this user. The user decides to send this data to the car, but the car moves away. This data is lost. And what's more, the user has no way of knowing this because she's expecting a web response maybe in a few hours. So until then, she has no way of knowing this. So this is the most challenging end of the spectrum, where routing is difficult, and it's difficult to support even simple applications like email. And TCP and other protocols that we know and love simply break down in this environment. So that's the story with the mostly disconnected end. Now let's see what happens when you go to the mostly connected network, the other end of the spectrum. Here I'm actually going to make a distinction between Wi-Fi meshes and cellular networks. So let's first look at Wi-Fi meshes. These are the most common scenarios are places where there's a lot of infrastructure. Again, I'm showing that again with these Wi-Fi access points. So these form a mesh. And a mobile user, can potentially get continuous connectivity because she associates to an access point and starts sending data. But as she moves, she disconnects from the previous access point and associates to the next access point and so on. So say this user associates to an access point and now starts trying to send data. She might actually be disconnected for a few seconds. And this disruption occurs because the link between the user and the access point is unpredictable. This due to several reasons, because of multipath fading, because of, say, interference and so on. And even though these disruptions are only last for a few seconds, they can severely affect performance of interactive applications such as VoIP or even TCP-based applications. So even though there's a lot of infrastructure, it's still difficult to support certain kinds of applications. And then when you look at cellular network, this is a different technology compared to Wi-Fi meshes. Here, the problem is that one cell tower usually provides connectivity to a large geographical area. And which means a lot of users are going to connect to the cell tower to connect to the internet. And because the cell towers usually have a limited spectrum, a user may not get connectivity. So the problem here is spectrum overload. And this actually is becoming quite a bit of a problem. There's been a lot of press coverage about how iPhones are overloading the AT&T network, as a result of which there are drop calls and spotty services and so on. So the takeaway from the last couple of slides is that there is unreliable connectivity across diverse networks that can hurt application performance. So the question is, how can we overcome unreliability? And so my work is about how we can provide ubiquitous access across these different network environments. And of course, we cannot support all applications in all of these environments, but can we support email in DTNs, say web search in intermittently connected networks, and something like VoIP in mostly connected networks? So today I'm actually going to focus on 3 specific protocols on 2 ends of the spectrum. I'll first talk about RAPID for DTNs. So remember, DTNs are where there's no infrastructure and there's unpredictable connectivity, and RAPID overcomes this to deliver packets. And then on the other end of the spectrum is Wi-Fi for Wi-Fi meshes, where there is a lot of infrastructure, but there's still disruptions caused due to unreliable links. And then I'll describe a protocol called Wiffler that's used to reduce the spectrum load on cellular networks. So the protocols I'm going to talk about, at least RAPID on one side and Wiffler Wi-Fi on the other side, are used to support different kinds of applications and are deployed in different environments. But the main problem is unpredictability. And so I'll also talk about how we can use utility-driven probabilistic algorithms to overcome this unpredictability. So the outline of the talk is going to be as follows. I'll first talk about RAPID for DTNs, and Wi-Fi for Wi-Fi meshes, Wiffler for cellular networks. And then I'll go on and very briefly talk about some of my other contributions as well as future work. So I'll start with RAPID. So the idea here is that there is, again, the basic premise is that there's a village and a user wants to send some data in the village, and there's a city where there's infrastructure. And say a vehicle comes within range, the user sends data to this vehicle, but the vehicle moves away. What happens is that the user waits for another vehicle to pass by and replicates this data to this other vehicle as well. By replicating, I mean making copies of the same packet. And then the replicated packet is then routed until it reaches the destination. And so notice that if I'd only used forwarding, that is, I only used one copy of the packet, this packet would have been lost. But because I've used replication, I can overcome unpredictability. And this is actually not our idea. This has been used before. In fact, Amin had worked on epidemic routing that used replication for DTNs. But the problem here is that you're flooding the network with the same copy of the packet, which may be fine if you have one user with one packet, but it quickly becomes a problem as you have multiple users trying to send multiple packets. So, to overcome this problem, we actually first formulate the DTN routing problem as a resource allocation problem. And this, notice, is fundamentally different from usual traditional routing problems, which is a path computation problem, where you're trying to compute the shortest path between the source and the destination. Instead, here, we look at it as a resource allocation problem, where the resource is the bandwidth during a transfer opportunity. What I mean by that is, say there are two nodes X and Y, both of them have a bunch of packets that they need to deliver. When X and Y are within range, we call this a transfer opportunity, and they can send packets to each other. And in vehicular DTN settings that we are considering, this transfer opportunity is one of the main resource constraints. Because when two nodes meet, there's only limited time they meet for, and so the total amount of data they can transfer is limited. So the question is, how do you allocate this limited bandwidth resource to packets so that you can optimize a routing metric? Or in other words, what we want to know is that given a set of packets, what subset of packets should I replicate during a transfer opportunity to optimize a specified routing metric? So for example, if I have 10 packets and I can only replicate one because the transfer opportunity is short, which packet should I choose? Because if you choose the same packet over and over again, the delivery rate of that packet improves, but all others would suffer. And the key here is that we want to optimize a specified routing metric. So we want to tune our replication according to the routing metric. So your routing metric could be, for example, minimizing average delay, or if you want to send news articles that expire within a deadline, then it could be you want to maximize the number of packets delivered within the deadline. So question is, how do you optimize a specified routing metric? We do this using a utility-driven algorithm, where we translate the routing metric to a per packet utility function. So once you have this utility function, you can estimate how much improvement in utility you can get by replicating the packet. And then you replicate the packet that gives you the highest improvement in utility, which translates back to a highest improvement in the routing metric. So before I go into details of how you would estimate these utilities or even define these utilities, let me go through how RAPID works very quickly. So you have two nodes X and Y. They are within communication range. The first step is the control channel step, where you send X would send metadata to Y. And I'm actually going to ignore this for a moment, and I'll talk about it a little bit later. The next step is direct delivery, where X would deliver packets that are destined to Y. And the third step, the most important one, is replication, where X sorts packets in its buffer according to the marginal utility of replication, where the marginal utility is the change in utility because of replication divided by the size of the packet. And it would start replicating in this order until either all packets are replicated or the nodes are out of range. And clearly Y would do the same to X. So this is how RAPID works, but the main question is how do you define these utilities and how do you estimate increase in utility? So our goal, remember, was to translate the routing metric to a per packet utility function. And so we loosely define utility as the contribution of a packet to the metric. So for example, if your metric was minimize average delay, then the utility is the expected delay of the packet. If your metric were maximize the number of packets delivered within the deadline, in the news article case, we define utility to be the probability of delivering this packet within the deadline. And then when you want to replicate, you estimate which packet would give you the highest improvement in probability in delivering the packet. And then you replicate that packet according to it. So let me give you a very simple example of how you would estimate these utilities. And I'm actually going to make a lot of assumptions here that may not hold in practice, so just bear with me for a minute. So say there are two nodes, I and J. There is one copy of I in the system. There are two copies of J in the system. And say nodes meet with uniform exponential meeting time with mean lambda, which means that the expected time for any two nodes to meet is lambda. And let's say I and J were created at the same time, t units before, and the deadline of I is less than t, so the I has already passed its deadline, but the deadline of J is t1 greater than t, so J is still not, it's not past its deadline. Now, let's say another node Z comes within range of X, and X can actually only send one packet during this transfer opportunity. The question is, should X replicate I or J? Now, this is the core, this is the question that RAPID is trying to answer. So, if my metric was minimize average delay, then remember that the utility is the expected delay of I. And so, we want to estimate how much change in utility by replicating I, so by going from one copy of the packet to going to two copies of the packet in the system because of replication. Because we've assumed uniform exponential meeting time with mean lambda, this means that your delay is actually going to reduce by lambda over 2, and therefore your marginal utility of replicating I is lambda over 2. I'm actually not going into details why this is the case, but believe me that this is what happens. Now, if I want to replicate J, I'll be going from 2 copies of the packet to 3 copies of the packet. So how much does my delay decrease by going to 3 copies of the packet? Again, because of uniform exponential meeting time assumption, the marginal utility is lambda over 6. And this sort of makes intuitive sense because the more replicas there are in the system, the less is the marginal utility of replicating, making more copies of this packet. So in this case, because it's the marginal utility of replicating I is higher, you would replicate I. But if my metric was maximize the number of packets delivered within deadline, then clearly there is no utility to replicating I because I has already passed its deadline. There is some utility to replicating J, which is the improvement in probability of delivering J within the deadline. And so here you would replicate J. So this is just a very simple example to show how RAPID can tune its replication according to the routing metric. But of course, I made a lot of assumptions here that don't really hold in practice. So the question is, how do you implement RAPID in a decentralized environment where there are several challenges? The first is that delay distribution is unknown. I assume the uniform exponential distribution, that may not be true. We don't have a global view of the network, so I don't really know that there are 2 copies of J. And feedback is delayed, which means that I might be replicating the same packet over and over again, even though it's already delivered because I just didn't get the acknowledgement fast enough. So to handle this, we use RAPID's control channel. So remember, when two nodes met, they exchange meta information on the control channel. So they first exchange node intermeeting times, so the expected time for any node to meet every other node, and nodes learn the delay distribution based on these intermeeting times. They also exchange information about packets in the buffer so that you can build a local snapshot of the global view. And they exchange acknowledgements of delivered packets so you can quickly remove delivered packets from the system. So I'm actually not going to go into details of how this control channel works, but the basic idea is that you want to exchange meta information to build a local snapshot, and in our experiments, the control channel contributed to about 1 to 5% of the total data. So this is how basically RAPID works. I'm actually going to take a small detour to talk about some analytical results that we have. So remember earlier I talked about how we formulated this problem as a resource allocation problem. Now we prove two results about this resource allocation problem. The first one is that if you have complete knowledge, if I knew future meetings, I had information about future load, and I had global view, then solving this DTN routing problem optimally is NP hard. And we actually also show that the lower bound on approximability is square root of n. The next result, and this is the more interesting result, is if you only had partial knowledge. Suppose I had global view and I knew future load, but I did not know what the future meetings were. Then we prove that any DTN routing protocol can perform arbitrarily far from optimal. In other words, if I only have partial knowledge, it's not possible to design a DTN routing protocol that performs even close to optimal. And we use a competitive hardness result analysis to do this. So, but empirically, we show RAPID comes within 10% of the optimal for low loads for which we could compute optimal. Unfortunately, we couldn't compute the optimal for higher loads. Okay, so that's the end of detour. So I'm going to now talk about how we evaluate RAPID. We evaluated it by implementing it on the DieselNet DTN testbed. So this is a testbed that consists of 40 buses that go around the campus. And these buses are equipped with a computer, a GPS, an access point, a 3G modem, etc. When two buses are within communication range, they can send data over the wireless access point. And so on the left, you see a snapshot of the areas that the buses cover, and the red spots are places where they were able to exchange information. So we deployed RAPID in this testbed for 58 days. And this is actually one of the first DTN routing protocol to be deployed on a real testbed at the scale. And then during this deployment, we also collected traces of how much data, like of bus meetings, like the time the bus meeting occurred, how much data they were able to transfer. And we used these traces to then run trace-driven simulations. Now, as a first step, we validate our simulator. So we make sure that the results we get from the trace-driven simulator is similar to the results we get from the real deployment. So here in this figure, the y-axis is average delay, and the red bars are results from the real deployment, and the green bars are results from the simulator. And as you can see, they match up quite well for the 58 days. And the simulator code and the RAPID deployment code is released, and other people are using it right now. So now that we have a simulator, we wanted to compare the performance of RAPID with other DTN routing protocols. Specifically, we compare it with random, which randomly chooses packets during a transfer opportunity to replicate. And then we used spray and wait and max prop. These were the state-of-the-art DTN protocols when we did this work. And both spray and wait and max prop are protocols that specifically try to minimize average delay. So they don't really tune other routing metrics. So I'm only going to show you two example evaluation results. So when we chose the metric to be minimizing average delay, so naturally the y-axis is average delay, the x-axis is the load. and we compared the performance of RAPID with other routing protocols. So RAPID outperforms the other 3 routing protocols, but also notice that because max prop and spray and wait are designed to minimize average delay, they do better, much better than random. Now, if I switch this metric, and now I choose my metric to be minimize maximum delay, and clearly this is a different experiment where RAPID is tunes its replication according to this metric. Here again, the y-axis is max delay. Again, we notice that RAPID outperforms the other 3 routing protocols, but also notice that because max prop and spray and wait do not tune their replication according to the metric, their performance degenerates to that of random. So in summary, I just presented the routing protocol called RAPID, which is a utility-driven resource allocation protocol that can be tuned according to a given metric. So that brings us to the end of DTNs, and now I'm going to move to Wi-Fi meshes. Before that, I just want to take a small break to see if anybody has any questions. Yes. Yeah. Oh, I absolutely do. I don't have it right now, but yes. Absolutely. So the RAPID has the highest overhead, which is 5% of the total data. And max prop has a little bit less overhead because they also exchange meta information. And spray and wait actually has no overhead at all. But then notice that when I'm presenting these results, they take overhead into account because I can only use bandwidth that is remaining after I send information on the meta channel. Okay, so let me continue. So I'm going to go from DTNs, where there was no infrastructure or very little infrastructure, to Wi-Fi meshes, where there's a lot of infrastructure. So here, again, like I mentioned before, the scenario is that there's a user associates to an access point and wants to send data to the internet through this access point. So, but then as she begins to send data, she realizes that she's disconnected for a few seconds because the link between the user and the access point is unpredictable. And even though this disruption only lasts for a few seconds, they can really affect performance of VoIP or TCP applications. So the idea here is that because this is the wireless channel and actually data has been sent in all directions, so assuming you have omnidirectional antennas, it's possible that other access points in the vicinity can overhear the packet. By overhearing, I mean receiving a packet that is not meant for you. So the question is, can we somehow leverage this overhearing to overcome unpredictable links? But before we answer this, I first wanted to see how the potential for doing this. So how much improvement can we possibly get by leveraging overhearing? Or does it even make sense to do this? So to answer this question, we conducted measurements on 2 test beds. The first test bed is in Redmond, where we deployed 11 access points in the Microsoft campus. So these red thumbtacks are positions of access points. And 2 vans, Microsoft vans, they go around the campus and they act as mobile nodes. And then the other test bed was in Amherst. And here actually we did not deploy the access points. I just used open access points that were already deployed. And the DieselNet buses act as mobile nodes here. So the goal for this measurement was to see whether nearby access points do overhear, and also is there potential to leverage this overhearing. And we found that in fact, indeed, multiple access points overhear a packet, not only in Redmond where we deployed it, but also in Amherst where we used organic access points already available. And we also found if you had an ideal scheme that could leverage overhearing, it significantly reduced disruptions. But this was an ideal, impractical scheme. So then, based on this measurement, our job was to translate these benefits you get from leveraging overhearing in a decentralized environment. So basically, design a practical protocol that can leverage overhearing. So as it turns out, this is not very simple. So for example, there's a mobile node that sends some data to, and 3 access points say overhear this packet. Now what should they do? Should all 3 of them send this packet to the internet? The answer is no, actually. Our first goal was we wanted as few relays as possible because bandwidth was limited between the, often bandwidth was limited between the access point and the internet, and also we wanted to reduce collisions. So we wanted to ideally run a consensus or a coordination among these access points so that only few of them would relay this. And we wanted this coordination to be fast. So we don't want to run a consensus algorithm because we want to support something like wipe. And we wanted it to be effective in the sense that the one that finally relays the packet should actually be able to successfully relay the packet. So there has been some related work in leveraging overhearing in static mesh environments rather than the mobile environment I'm looking at. And they either assumed unlimited bandwidth between the access points and the internet, or they only support slow coordination because they were based on batching. Neither of these was suitable for this environment where we are trying to support VoIP. So in Wi-Fi, we use what is called as probabilistic relaying. What I mean by probabilistic relaying is, suppose there's a source and a destination, and there are a few access points around. The source sends some data, the destination doesn't hear it, but A and B overhears this. Now, clearly the destination is not going to send an ACK back because it did not hear the packet. This is the link layer ACK, by the way. And so then A and B would probabilistically relay this packet to the destination. By probabilistically, I mean A tosses a coin. If the number is less than RA, it would send the packet, otherwise it will not. So clearly you can see that there is no coordination involved. They just toss a coin and make a decision. But the problem, of course, is how do you design, or how do you decide what your relaying probability should be? So, but before I go into how to decide what the relaying probability should be, I want to take a small detour to talk about why is it that relaying is effective in the first place. So basically what I'm saying is that the source sends some data, the destination doesn't hear it. Now instead of the source retransmitting, I'm going to let A or B send this data to the destination. And this is effective, and this is based on some measurement study we did, and it's also been corroborated by others, is that losses are bursty in this environment. Which means that the source sends some data and then it retransmits again. There's a chance that this the retransmission also will fail. And also, most losses are path dependent, not receiver dependent. In other words, if the source sends some data and destination doesn't hear it, it's completely independent of whether when A or B sends the data, the destination will hear it. So these are some of the reasons why relaying is effective. So let's get back to how you would actually estimate these relaying probabilities. So A has to figure out with what probability it should send a packet. Notice that this relaying probability is actually a trade-off between having too many relays. Suppose my relaying probabilities are too high, everybody will decide to send data and you will overload the network. And having too few relays, because if the relaying probabilities of all the neighbors is very small, then nobody will relay and you won't really be leveraging overhearing. So to estimate these relaying probabilities, we follow the following guidelines. The first is that you want to account for relaying decisions made by neighbors. In other words, if all my neighbors have very high relaying probabilities, I probably should have a smaller relaying probability. You want to prefer access points that have a better connectivity to the destination because that means that you're going to be effective in your relaying. And you want to limit the expected number of relay transmissions. In other words, I don't want everybody, I want expected number of relays to be some small number. Now, there are multiple ways in which you can formulate the problem that satisfies these guidelines, but the one formulation that we found was most effective was the following, where each individual access point would relay packets such that collectively the expected number of relays is 1. So we want to limit the expected number of relays to be 1, and we want the relaying probability is weighed according to the access point connectivity. So let me give you a simple example of how say B would compute its relaying probability, B would first, so it wants to make a collective decision. So it would first estimate the probability that its neighbors are all also considering relaying. So for example, its neighbor A is considering relaying, which is the probability that A heard the packet but did not hear the ACK. And so based on this, the expected number of relays by A is the probability that it's considering relaying times the probability that it relays the packet. So it's CA times RA. Now, B would solve this equation that the expected number of relays across all of its neighbors is equal to 1, because that was what our objective was. And in this case, where there are 3 nodes A, B, and C as neighbors, this equation is CA times RA plus CB times RB plus CC times RC equal to 1. So if B, notice that if B solves this problem, it not only determines its own relaying probability, but also the relaying probability of its neighbors. And every node is doing the same thing, which means that all nodes are estimating their own relaying probabilities plus that of the neighbors, and the probabilities work out in such a way that they all make consistent decisions. So here, of course, this is an under constraint equation. So to solve this uniquely and also according to our objective, we set the relaying probability proportional to the probability that the access point can actually deliver the packet. In other words, we weight the relaying probability according to the connectivity of the access point. And also here I want to mention that some of these probabilities, for example, the probability that A heard the packet but did not hear the ACK, etc. To estimate these, what we do is do some sort of an online measurement of connectivity. So every node maintains its transmission rate or success rate with every other node. And to do this, actually, we don't have to do anything extra. We just use 802.11 beacons. And then every once in a while, we send this information to all our neighbors so that the neighbors know my success probability with every other neighbor. Okay, so that's how basically Wi-Fi works. We again implemented and deployed Wi-Fi in the Redmond testbed, just like we implemented and deployed RAPID on DTNs. And we also ran a trace-driven simulation in the Amherst testbed. And our evaluation criteria were, does Wi-Fi reduce disruptions? Because that's what we started out with. Does Wi-Fi improve performance of interactive applications such as TCP and VoIP? And finally, is Wi-Fi's probabilistic relaying efficient? In other words, am I making sure that there aren't too many relays in the system? So in the interest of time, I'm only going to describe one evaluation. This is for Wi-Fi, the VoIP performance using Wi-Fi in the Redmond testbed. And we used a G.729 codec, so which means it translates the VoIP voice into 20 byte packets at a 20 millisecond interval. And our metric was the average length of a call before a disruption. So how long can I continue talking without being disrupted? And we compared Wi-Fi with today's protocol, and we find that Wi-Fi actually doubles the length of a call before a disruption. So in summary, I just presented Wi-Fi, a practical protocol that uses probabilistic relaying to leverage overhearing. And I just wanted to mention also that this idea of probabilistic relaying has since been adopted by others to design other mobile mesh protocols. Okay, so this brings me to the cellular environment, which is also a well-connected environment, but it's a different technology compared to Wi-Fi meshes. And again, I'm going to take a small break to see if anybody has any questions. I can actually not see the audience now for some reason. Actually, we don't. We just assume that if it's a hidden receiver. So you mean if it's a hidden terminal, then I would not have a good estimate? So, I mean, the one thing we do is that take into account that others are also sending me information, right? So if there's another node that can overhear this, say X is the hidden terminal from me. And then there's another node that also hears from X, then it can give me the information. But actually, right now, we don't take that into account at all. We just ignore this problem. Okay, I'll continue. So, so this is for the cellular networks. So I'm actually going to very briefly talk about Wiffler. I'm not going to go into too much details. So the idea here is, so I mentioned the problem before was that cellular networks were overloaded. They had limited spectrum. And we wanted to see if we can somehow augment the spectrum with open Wi-Fi access. So what I mean by this is as follows. So there is, say, a user connected to the cellular network to connect to the internet. Now, as this user passes through an open Wi-Fi access point, she can shift from the cellular network to the Wi-Fi access point and start sending data. And so clearly the load on the cellular network is reduced, but also Wi-Fi usually has small range, so which means that very soon you're going to move out of range of this access point, and when she connects back to the cellular network until she meets another access point. So this is the basic idea, and of course the question is, even before you design a protocol that will do this, is how much data can you possibly offload to an open Wi-Fi access point? I mean, does it even make sense to do this? So to answer this question, we conducted a measurement study, a combined 3G Wi-Fi measurement study in 3 different cities, in Amherst, Seattle, and San Francisco. And what I did was I equipped a vehicle, a car or a bus or what have you, with a computer, a GPS and a Wi-Fi radio as well as a 3G modem. And the software would continuously, simultaneously send data both on Wi-Fi and on 3G. And the idea was to find out both what the availability was and what the performance was. So the chart I'm showing here shows the percentage availability in the 3 different cities. So first notice that the average availability of 3G is about 85%. So it's not actually even close to 95%. So it's not as ubiquitous as you would think. And the average availability on Wi-Fi is about 11%, which is actually much, much lower. But I was still surprised that I thought 11% was still high for connectivity with open access points in 3 cities. The other thing that we noticed in our measurement was that Wi-Fi performance in terms of throughput and loss rate was much, much poorer than 3G. And again, this is surprising in that in stationary environments, Wi-Fi performance in terms of throughput is much better than 3G. But in mobile environments, we found that it was much worse. So the results from this measurement study is that if you, at most 11% of data can be offloaded to Wi-Fi because that was its availability, and further offloading may affect performance because Wi-Fi performance can be poorer when you switch. So, okay, based on this measurement study, we designed Wiffler. And the goal in Wiffler is as follows. We want to maximize the total data that we can offload to Wi-Fi, because that means that we are freeing up 3G spectrum. But we want to do this without affecting application performance. So to do this, we actually look at 2 different classes of applications. We first look at delay tolerant applications. One example of a delay tolerant application is email. But what I mean by this is that you can tolerate a few seconds delay. The application will not suffer very much. So the idea here is that, like if I can wait for 20 seconds, then Wiffler would wait for those 20 seconds to see if it can send data on Wi-Fi. And if it cannot send data on Wi-Fi, then only then will it start to send data on 3G. And what Wiffler does is one step further, where it predicts whether in the next 20 seconds Wi-Fi is going to be available and only waits if Wi-Fi is going to be available. Otherwise, it switches to 3G immediately. So in other words, you only delay applications if it's going to be beneficial in terms of 3G savings. And then for loss-sensitive applications such as VoIP or say video streaming, the problem here is that if you switch to Wi-Fi whenever it's available, the performance you might affect the performance of the application because Wi-Fi performances can be poorer. So here we switch back to 3G when we find that Wi-Fi performance is poor, but we actually have to do the switching at a very small delay granularity because otherwise there's no use in doing the switching because VoIP is anyway, for example, VoIP application is anyway maybe dropped, for example. So here we actually use a delay threshold of 40 milliseconds, and to implement this, we did this at the link layer where we have a signaling mechanism where within 40 milliseconds of sending data on Wi-Fi, I don't get a link layer ACK back. I signal the higher layers, and the higher layer then starts to send data on 3G. So again, we experimented this with for VoIP. I'm actually not going to go into details of how, for example, how we did the learning, etc. But I'll quickly show you some evaluation. We implemented and deployed Wiffler in the Amherst testbed, and I'm going to show you evaluation for two different classes of applications. One was web browsing, the other is VoIP. So for web browsing, what we did is we got traces for web browsing from real commuted buses. And here the y-axis is the fraction of data that you can offload on Wi-Fi. And the bigger it is, the better it is for us because that means we're reducing 3G load. And the x-axis is delay tolerance. And we compare the performance of Wiffler with a protocol that uses Wi-Fi only when it's whenever it's available. So in other words, it won't really wait for Wi-Fi to become available in the future, and therefore it doesn't really leverage delay tolerance. So if you don't leverage it at all, the amount of data that you could offload in this experiment was 22%. But then if you did use Wiffler, you could actually offload 52% of the data if you had a delay tolerance of 100 seconds. And here I also wanted to mention that I'm not showing this on the graph, but the total amount or average time that applications were delayed because of Wiffler was about 15 seconds, more than what you would have been delayed usually. Now, so another class of applications is VoIP, which is a loss-sensitive application. Here, the problem was that if you switch to Wi-Fi whenever it's available without considering the performance, then the application performance may suffer. So to see that, the y-axis here is the percentage of time that the VoIP quality is good. And we compared performance of Wiffler with a policy that uses Wi-Fi whenever available without taking into account the performance. So you see that so if you use Wi-Fi whenever available, only 40% of the time is the VoIP quality good. On the other hand, if you switch to 3G whenever you find that the Wi-Fi performance is poor based on not receiving a link layer ACK back, for a switching threshold of 40 milliseconds, for example, the percentage of time that the VoIP quality is good is about 72%. And of course, if your delay threshold is higher, so you keep taking longer and longer time to switch to 3G, the VoIP quality keeps getting worse. So in summary, Wiffler augments 3G spectrum with Wi-Fi, and it does so without affecting application performance for applications that have very high QoS requirements by exploiting delay tolerance and by using fast switching. Okay, so that brings me to the end of Wiffler. I'm going to move on to some of my other contributions as well as future work. And of course, I'll again stop for a little bit to see if anybody has any questions. Sure. What I did was on Mad Wi-Fi, I introduced a signal, and what the signal does is as soon as I get a link layer ACK back, it lets me know. And so if after 40 milliseconds I don't get a link layer ACK back, I start to send data on 3G. So I do the sending data on 3G or Wi-Fi is done at the application level. Hello? Yes. Yes, yes. Well, yeah, we did not take energy into account here, but yes, you're right. At least in terms of, so 3G Okay, let me put it this way. 3G is always connected, and Wi-Fi is connected whenever I get the Wi-Fi access point. And so with 3G, actually, keeping it connected is not a big deal in terms of energy. It takes very little energy to maintain the network connectivity, but in Wi-Fi, it is a problem. So you may have to do something like due recycling or something like that so that you're not connected. So in this case, it was not a problem because we were only when we were connected to Wi-Fi, we were sending data. But if you don't want to do that, you have to do something a little bit smarter. Sure. I agree with you. So like I said, with Wi-Fi, we have to do something a little bit smarter if we want. In this work, actually, we did not take energy into. Energy was not one of the issues that we were considering. But yes, you're right. Yeah. Uh, that, that's a good question actually. So right now we don't. We basically punt on the question. What we do is have a proxy that we connect to. So on the other end, the application is still running and unchanged, but we have a proxy that collects this data and then sends it across so that we can maintain the same IP address. I mean, you can do certain things, like for example, if it's HTTP, you could use HTTP range requests and send one set of range on Wi-Fi and the other on 3G. But right now we use a proxy. Okay. Actually, I'm not able to see the audience. Is there any reason? Okay, that's fine. Oh, I see. Okay. Actually, you can bring it back. I will minimize it on my end if that's okay. Okay. So let me continue. So I want to briefly go over some of my other contributions as well as talk a little bit about some future work. And I'm actually going to do very brief description of that as well. So I talked about how the goal was to improve connectivity across these diverse network environments, and I talked about RAPID, Wiffler, and Wi-Fi. For intermittently connected networks where your disruptions can last for a few minutes, I designed a protocol called TEDU. So TEDU is an application level proxy that uses some IR techniques to make sure that web search will work in this environment. And I also wanted to point out here that without TEDU, actually, web search will completely break down if you have intermittently connected networks where disruptions last for a few minutes. And then more recently, I've been working on this problem of energy because mobile devices are energy constrained and they're small and they're usually battery operated. And here I also wanted to just mention briefly that the Wiffler work that we did there, the model was not mobile phones, it was more laptops. So, and in fact, all of the implementation we did was on laptops. But for mobile phones, this is more of a problem. Energy is more of a problem, and there are different components that require energy: the network interface, the processor, the sensor, and so on. So, for reducing the energy for the network interface, we designed a protocol called Tailender that reduces actually the cellular energy cost in networks. And then for processor, we designed a protocol called MAUI. The idea in MAUI is that you offload code from your mobile phone to a nearby infrastructure so that the infrastructure runs this the code and the mobile phone's processor doesn't have to run it, and because of which you can reduce the total amount of energy on the mobile phone. And finally, in the sensor network space, I'm currently working on an animal monitoring project called TotalNet. And here, this is also an energy problem where, so we have gopher tortoises deployed in Mississippi, where the tortoises are equipped with a sensor, a solar-powered sensor node. And so the solar powered sensor would harvest data but the amount of data that you harvest keeps changing, so you have to adapt the amount of energy that you use for sensing and routing according to the amount of data that's available. So those are some of my other contributions. Let me talk about some work I want to do in the future. My main goal is that I want to make mobile computing ubiquitous. In other words, enable seamless operation and improve usability of next generation mobile devices. Now, there are several challenges that you need to tackle to solve this problem, and I'm specifically interested in or looking at 3 challenges. The first one is that of non-adaptive protocols. So basically, protocols that are designed for one environment will completely break down in another environment, and so this clearly affects seamless operation. Because, say, I talked about these different environments, the well-connected networks, DTNs, and so if the protocols break down, the user cannot move from a DTN environment to a well-connected environment. So, for example, I talked about how replication was useful in DTNs, but replications are likely to be less useful in mesh environments where there might be a lot of congestion. So how should a user tune replication as she moves from a DTN environment to a well-connected environment? So similarly, another example is I talked about how Wi-Fi performance in mobile environments is much poorer compared to stationary environments. This is because, again, protocols are designed for Wi-Fi are designed mainly for stationary environments. So how do you adapt as the user moves from a stationary to a mobile environment? So this is this flavor of work I want to do in the future, which is how do you design self-adapting protocols? The second challenge is energy limitation. And this actually seriously affects the usability because it restricts the kinds of applications you can deploy on mobile phones. Here again, one of the things I want to focus on is, so mobile devices have multiple interfaces, Wi-Fi, 3G, Bluetooth, what have you. They usually have complementary energy profiles. So at some instance, it might be better to send data on Wi-Fi. Another instance, it might be better to send data on 3G. So the question is, can we have one virtual interface that will decide which interface to use at that particular instant? And actually, there's been a lot of work on this, again, even at UCSD, but there's still more challenges remaining, I think, that I'm interested in working on. And then finally, one of the problems in designing mobile protocols today is that we have limited understanding of user behavior. So we don't really know how users use their phones, what sorts of applications they run, how much data they actually send, and so on. Because of which it's difficult to first design next-generation protocols, but it's also difficult to evaluate current protocols with respect to real users. So here I want to explore the possibility of designing an evaluation platform that will help evaluate new protocols with respect to real users. So these are some of the things I want to work on in the future. But before I summarize, I want to thank my collaborators. I've had the good fortune to work with some wonderful collaborators, my advisors, Brian and Arun, other folks at UMass, Niranjan, Mark, and Jacob. And at Microsoft Research, I was interning for 3 summers, so I worked with a bunch of people there, Rapul, Victor, Stefan, and Alec, and at Duke University with Eduardo. So to summarize, the goal of my work was to provide ubiquitous access to mobile users across diverse environments. And so I presented decentralized probabilistic algorithms that reduce disruptions in these diverse network environments, and specifically spoke about DTNs, Wi-Fi meshes, and cellular networks. And in future work, I want to design protocols that can now adapt seamlessly as users move between these different environments, as well as improve the usability of mobile devices. With this, I conclude my talk. I'm happy to take questions. Thank you.